Well, thanks again for inviting me. I actually was really looking forward to attending in person, but unfortunately, there were some last minute unexpected issues. I still hope I can probably visit Rikin sometime soon, maybe this year. In any case, I'm really happy to talk about this topic today because it's also something that we are actively involved with colleagues from Japan, Rio Yokota here, and try to give a kind of overview of ongoing activities and some open source AI projects that we kind of collaborate on, and it involves open source communities from multiple countries, and it's very exciting kind of times when the open source seems to be catching up, and who knows, maybe we'll even get ahead of state-of-art large-scale systems in industry. But back to the topic, so the role of high-performance computing in building truly open AI. That's what I would like to kind of discuss today. And starting at a high level, what is the whole field of AI really up to? Everybody would like to build not just narrow, excellent AI systems that can do specific tasks well, not just like systems that can only play game of Go or only play game of chess, or maybe only generate kind of images and so on and so forth. But we would like to eventually build systems that are to some extent as general and versatile as humans are, even though they might not necessarily be beating humans in all aspects of each task, but they have to be generalist agents. And it's kind of one of the common definitions, practical definitions of what people mean by artificial general intelligence, just kind of quoting OpenAI, high-level definition that it's highly autonomous system or collection of systems that, perform as well or outperform humans at most economically valuable work. So basically, that's a definition of useful multitasking. I don't want to go into kind of argument about how to define AGI, because if you go on Twitter or any other social networks or kind of participate in those arguments with AI people and not AI people, definitions vary from anything, as I said, very practical as multitasking system to something completely mysterious as a conscious being or whatever. So I'll stick to a more practical definition as a system that can be generalist, that can transfer across very different data sets and tasks. And in that sense, what's going on right now with large-scale systems is definitely getting closer to AGI in that definition. So until recently, and actually still to be kind of completely tested and make sure that it doesn't happen in large-scale systems, the problems that kind of really were slowing down applicability of AI systems were all kind of instability, lack of robustness and kind of sensitivity to various type of input perturbations where there are adversarial kind of noise added to systems specifically to kind of make them make mistakes, or distributional shifts, the classical examples of system learning about animals and trying to classify cows versus camels, but latching on properties such as background, color, and then being unable to generalize in presence of different background like cows on the beach. So all this kind of lack of robustness and lack of transfer between domains and lack of distribution out of generalization can be quite dangerous if you start applying those systems in real life to situations where the background and kind of environment changes very quickly, and you need to adapt to new situations like autonomous driving on country road to highway to city, but you also don't want to forget what you learned before. So you really need to have some form of continual learning. Same applies to chatbots if you want to apply them in multiple settings, even for the same person, leave alone trying to transfer what they learned from one person to another. Yet another example, and there are many others, is say healthcare, medicine. That's something that kind of one of the applications that I'm involved in and interested in historically since my work in IBM. And the data sets from different hospitals and different subjects vary, and from different equipment vary enough to usually present a challenge, generalization and transfer challenge to those AI systems. So basically, this is all about what was the whole artificial intelligence, machine learning, and even going back in history, statistics, what it was always about. It was always about improving generalization. It's just the notion of generalization was expanding from generalization within the same data set, like in statistics with IID samples, to switching between different data sets and doing the out of distribution generalization, and then moving further and further, out of distribution towards generalist agent. And there are many fields of machine learning that all kind of share the same goal, but may differ in terms of particular settings. So recently, we all witnessed in the past couple of years what one can call scaling revolution. Essentially, large-scale systems beating the state of art in multiple kind of settings and applications, and definitely demonstrating generalization as never before. So perhaps scaling might help us solve that kind of holy grail of the AI, machine learning, and statistics, generalization and transfer. And as you probably have seen, since November when ChatGPT came out, the race across AI labs and industry is becoming more and more kind of intense because ChatGPT really attracted so much attention and so many people kind of using it for various applications that now, the competition is intense and chatbots started appearing kind of from different companies, one after another. So it's kind of only getting more and more interesting. And it all kind of started, again, I probably shouldn't even explain it here, but it's all started with this GPT-3 model in May 2020, and then followed up by models such as Clip, DALL-E, then Copilot, basically going beyond language towards multimodal models with images and with code generation. And more recently, there is a whole explosion of those models that I'm not even kind of listing here. But the idea is that if you manage to pre-train large models on large amounts of data, the hope is that they will be better and better as a basis or like foundation for building applications on top of them with even smaller amounts of data that you can use to fine-tune those models and apply them in whatever domain you need. And indeed, the kind of huge difference in the performance apparently mainly came from the huge difference in size of the model and the amount of training data, because essentially the architecture was the same type of a transformer that was used before. So GPT-3 versus GPT-2 and previous kind of state-of-art models. So that was, as you probably all know, 175 billion parameter model trained on almost like 45 terabytes of training data. And essentially, it's like autoregressive model that predicts next word from the previous word. So what was so cool about that was that generalization, or few-shot learning, as you can call it, the fact that the model, once pre-trained, was able to very quickly adapt to new tasks by just seeing a few examples of that task. And the larger the model size, the better this generalization ability or few-shot learning ability was getting. Like this classical plot from that paper was showing how the accuracy would drastically improve with a number of examples, and there's a small number of examples for larger model comparing to the smaller one. So that was example where the size of the model apparently really made a huge difference. And there are other systems, as I mentioned. I mean, the list goes on. Clip was example of multimodal system where essentially you enter the image and you output the text, kind of describing the image. The system generalized zero shot and better than state-of-art systems before that to quite out of distribution data sets. So that was really impressive. And that was, again, resolving all these open questions in AI fields such as continual learning, meta learning, domain adaptation, transfer learning, out of distribution generalization. So now the scaling pretty much was kind of solving all these problems. And why scaling is important? Well, it's really important to look at scaling laws, or essentially see what the trends are, is that most of the time we see unusual trends kind of going against our previous common wisdom. For example, people used to say that convolutional networks indeed are the best type of, it was state of art for vision models, but essentially you can use something simpler, like this mixer, almost like MLP type of a model. And essentially at scale, with amount of data, the trend is such that the performance can reverse, and the systems which were kind of underperforming at smaller scale will be champions. Actually, they will be the state of art at larger scale. That's why tracking the performance using scaling laws, where the x-axis could be the amount of data or the size of the model or the amount of compute, is very important kind of investment tool in machine learning that we should definitely always keep in mind when we're trying to compare whatever novel models and algorithms. And the famous kind of paper from Jared Kaplan and collaborators from OpenAI that came out like in 2020 was essentially popularizing power laws of the scaling of those large models with compute, dataset size, and parameters. And this kind of classical by now plot was essentially telling you that if you on x-axis put, say, compute dataset size or parameters, and you allow the other two variables to be varied in unconstrained way, so you're not bottlenecked by them, then if you take the best result out of all models with those varying parameters, and you just plot it here, essentially you keep seeing straight lines on log log plots, which means, well, power law distributions of the test laws in this case. And then people observed similar kind of behavior, not just for test laws, but for also various behaviors for downstream tasks and so on and so forth. And that generated lots of excitement. 2021 was kind of the year when people started building huge models, thinking that essentially model size is all what matters. Because actually the paper by Jared Kaplan and colleagues from OpenAI showed, well, according to their experiments, that whenever you increase compute, you should increase the model size 5 times roughly, and the data size twice. So basically, it was suggesting that you need to grow the model more than the data. So you see, people were building like up to like 530 billion parameter models, like this Megatron, Turing, and so on and so forth. And then last year, there was an interesting discovery. There was so-called chinchilla scaling laws. It was a paper from also DeepMind that got the New RIPS, the top AI conference best paper award, which actually reconsidered the scaling laws with compute. And while the other two scaling laws, like with data and model size, remains the same, the scaling laws with compute actually could be much more kind of advantageous. So essentially what that paper was saying, that if you scale 50-50 model and data set size, then you essentially can achieve the same performance with much smaller models, but at the cost of investing in much more data, which is kind of making sense if the data set is much more informative. That model may be able to absorb that information even at smaller kind of scale. So anyway, so this is a recent kind of state-of-art scaling laws, and basically the paper explored the trade-off between the number of parameters in the model and training laws, and kind of showed that the best results will follow that kind of 50-50 rule that I'm mentioning here. So they also provide some useful charts for how much training data and compute you'll need to optimally train like models of different sizes. And jumping a little bit ahead, I didn't keep track of time. I just wanted to say that currently we are following this type of currently optimal scaling laws in a large-scale project on Summit that I will mention in a few minutes from now. But more generally, I just wanted to make a small diversion and say that important aspects of this whole scaling kind of experiments and scaling laws that help you decide which particular architectural choices and other kind of engineering decisions you should be following depending on what scales better. It's important to keep in mind that power laws are not always what the scaling is looking like. In general, the curves are having several kind of breakpoints, although soft breakpoints. Initially, the performance may not increase as fast when the model is too small or training data is too small. Then it kind of accelerates and you get into power law region, and then you may kind of asymptote. But also other behaviors are kind of possible, and people observed with GPT-3 some hard to predict performance kind of rapid performance improvements at certain number of parameters in the model. So-called sharp transitions in performance were always kind of puzzling to predict, and they didn't fit the usual power laws. There was more and more recent observations about such sudden transitions in the behavior, which attracted lots of interest of many kind of researchers. For example, grokking behavior with compute on x-axis when the fixed size model for the same data set essentially at some point suddenly improves its performance from practically a kind of 0 to 100% accuracy, for example. So there are multiple interesting recent developments in terms of scaling, which were not yet there a year ago. And for example, this paper on emergent abilities of large language models shows many empirical kind of results. Basically, it's a survey of papers which reported such results, where you see these sharp changes in their performance, which definitely do not follow directly power laws. That motivated recent work from my group led by Ethan Caballero, who is my PhD student right now, and myself and several collaborators on trying to capture the performance of scaling laws with more universal functional form. And it turned out that so-called smoothly broken power laws can be quite convenient, a generic, universal type of a functional form to rule them all, in a sense. And without going into too much details, because I might be also getting close to the time limit, just wanted to say that we were able to capture behaviors that were highly nonlinear, like double descent or even multiple descent in terms of generalization. We were able to predict and accurately predict, accurately extrapolate phase transitions, or like sharp transitions in performance based on the data before the transition, but sufficiently close to it, and so on and so forth. What I'm trying to say that in general, this whole field of studying how to predict scaling of your systems is completely essential when you will be in practice trying to scale them on large compute systems, and you really don't want to waste that compute. So you want to be as accurate as possible about predicting performance based on kind of smaller experiments. But switching gears a little bit, I just want to say that essentially the lesson in the AI development in the past decades was well summarized by short but very famous now article by Rish called The Bitter Lesson, that essentially the biggest lesson is that models that exploit too much of inductive biases and expert knowledge and so on and so forth, they do not stand the test of time, while the general methods that leverage computation ultimately are the most effective, and essentially scaling is, well, maybe not all you need, but definitely a a huge part of what you need to achieve state-of-art performance of AI systems. And this kind of plot from the Epoch AI, which actually focuses on forecasting AI trends, as well as actually compute trends, and it's really worth checking out as a website. I mean, they did great job doing forecasting and summarization of existing research, basically showing like where we are in terms of rapid increase in the compute for the state-of-art AI systems. And as you can see, there was a break in the trend around 2012, the so-called AlexNet moment of deep learning, when AlexNet kind of won the ImageNet competition by a large margin. So people started building larger and larger systems. And most recently, by 2020, you basically see like a huge increase in the amount of compute for building state-of-art models. Anyway, so there are some other recent statistics about the amount of basically compute that is taken to train state-of-art models most recently, where GPT-3 is, where Lambda is. Stable Diffusion actually is not that large and not that compute expensive as some other models. But you also see the interesting trend about academia versus industry versus research consortiums. And most recently, you basically see that number of large notable systems is to large extent also coming from research consortiums or like open source communities, which is interesting indeed, very recent trend. I'll talk about that soon. So bottom line is that perhaps in this kind of race towards AI that I mentioned before, perhaps compute plays crucial role. And that's why companies like OpenAI and Google and Microsoft are ahead of kind of academia, because they're able to train such large-scale systems. And the question is like how academia can possibly catch up with that, and how open source AI communities can catch up with that. So the question is, how can we possibly democratize AI so that AI becomes a commodity that anyone can use rather than a property of a few very large corporations? So yeah, how I'm doing on time, by the way?
If you can try to wrap up, it would be nice. Yeah. We still have the panel, of course, where we can extensively discuss.
Yeah, so I'll do that. But in any case, basically, I was saying that there is a rise of multiple self-organizing research, open source grassroots communities. And basically, there are two ways towards kind of catching up with industry. One way is to use private compute. For example, Stability AI is providing and growing their supercomputer. And another is precisely kind of what we're talking about here is government-funded public supercomputers. For example, Summit is what we're currently using, and we're using it in kind of collaboration with Eleuter AI and Lion. There are many other communities also there, and just wanted to say that it's really exploding grassroots movement. Well, Lion is known for its large-scale data sets, as well as a state-of-art CLIP model that beats OpenAI model. And essentially, currently they also are working on Open Assistant kind of competitor to ChatGPT, like Open ChatGPT. And here is our Insight project that I just wanted to highlight. We applied last year, and we're really happy to have it accepted, about scalable foundation models for transferable generalist AI, in collaboration with multiple people, as I mentioned, Lion Eleuter, and as well as Rio Yakota here. And essentially, we're focusing on building large-scale model following chinchilla laws right now, hoping to scale it way beyond 70 billion that originally DeepMind built. We also, second kind of line of projects focuses on multimodal generalist kind of agents. And finally, we focus on interactivity of those models so that they can actually learn continually, which is not exactly yet kind of property of those large-scale systems built in industry, but I'm pretty sure, well, I mean, everybody's working on that. So that's kind of roughly the scope of our Insight project for this year. And I'm probably going to skip the details, but I just wanted to say that we did explore how, say, GPT-Neo X version of the larger GPT scales. So far, we see very nice utilization of Summit resources. So basically close to optimal, and similar things are with multimodal models such as CLIP. So it's kind of promising, but we will keep like pushing the scalability kind of upper limit and see what happens, while also training multiple smaller models so we can plot those scaling laws and decide how to best invest in the future compute. But yeah, one last but not least, I think we're also trying to build models with some interactive fine-tuning so that they will not behave in unethical way and will not answer questions like, in this case, a small publicly available system, Magma, did. Yeah, we don't want the system to give such answers. Yeah. I'll skip the details about some other inspirations and basically just want to conclude here. So the long-term goal, we really would like to build large-scale state-of-art systems that are not just for research purposes, but for applications that are of importance to society, healthcare, and so on and so forth. And we want to do such this in a completely open way. We want to essentially democratize AI through those open source communities in academia. And that will clearly require access to large-scale computational resources. And that is why I think our applications for large-scale compute are extremely important for this whole community to keep doing what we're doing. Thank you very much.